Let's get a better understanding of how capacitors work in this question. Example, MJ16 P41 Q7. So a student sets up the circuit shown like this to measure the charge on capacitor C for different values of potential difference. Now a quick note, how do you measure charge Q? And why is this circuit set up like this? So if you forgot how to interpret this, this is kind of like a battery power source, variable power source with the arrow here. And on the left side, you have a voltmeter, and this is to measure not only this variable E, whatever power is set to, but also to measure the potential across this, potential difference across this capacitor. Okay, so that's V. Then you're gonna have current flowing, right? Current can flow here to charge up. Depending on if your switch is connected like that, then it can be charging. Or if the switch is connected this way, then the capacitor will just discharge this way and go back. So when there is current flowing through this meter, you can calculate Q equals to IT. So there are meters that can do that, and ammeter is one of the ones where we usually use to measure that. So, tip for you. You don't see much pass here in paper 4 for capacitor. That's because there are more of them in paper 5 experiment. So when you have an experiment to investigate capacitor, it often will look something like this. Measure V, measure A, power source, capacitor. Alright, let's move on to the experiment. Oh my, this definitely looks like paper 5. The variation with potential across the Q stored is shown here. Well, I guess we have to draw a graph later. But state and explain how the figure shows that there's a systematic error in the readings of one of the meter. How do you tell systematic error again? Kind of to remember your AS paper 2. So systematic error in terms of graphs means all the values are shifted above or below. So we look at this, okay, I roughly draw a line that's something like that. Now that's not a great best fit line, we'll draw a better one later. But if you notice, it doesn't exactly pass the the origin here. That's a problem. Why is that a problem? Because this is a graph of Q against V, correct? So Q equals to CV. And you're like, hang on a second, this is a straight line equation, y equals to mx. So there shouldn't be an intercept, there's no plus c, y equals mx plus c, it should pass the origin. So that's what you're going to explain here for 2 marks. You can say, firstly, the graph, or you can say what should be the correct one. So you can say based on the equation, Q equals to CV. Q should be proportional to V. That's what we know from the equation. Or you can say, when Q equals to 0, V must be 0. Any of this is okay, as long as you know what it should be the graph. But what's wrong with our graph? Then you describe. Oh, didn't pass intercept. So you can say, but graph has a non-zero intercept. That's the word for it. Non-zero intercept. Or in other words, you can say it does not pass through origin. Doesn't pass origin. There's 2 marks here. The first one is for the first point. What should be the graph, and why is this graph problematic? And says that, oh, there's a systematic error. All the values have been shifted down. That's why your y-intercept is there. It should not be there. Okay, so let's go next one. Use a figure to determine the capacitance of C. Ooh, use a graph. So we're really talking about graphs here. And you want to determine capacitance. Capacitance will be your gradient of a Q against V graph. So Q is the y-axis, V is the x-axis, so gradient will be C. So it looks like we'll need to do a best fit line after all. Okay, let's do a proper one. So a possible line can look like this, best fit line. How do you know? Roughly about 3 points above the line and about 3 points below the line, although they're a bit close. Let me adjust a bit. There, maybe that looks a little better. Okay, so what you need to do is similar to paper 5, just pick some points. Choose a nice point that passes through the corner, like maybe this one. Then the other side, you're like, oh, maybe I'll look for some points that passes through. Oh, you're like, oh, maybe the end passes through the corner. I guess this one. Okay, these are some samples. I won't do the whole graph reading on the screen, but you choose something to find your 2 points. So this will be x1, y1, x2, y2. Okay, so I'm going to skip. So on my paper, when I did the graph, I used these points. So you know that C is going to be the gradient. So you plug in your points, y2 minus y1, x2 minus x1. So my points that I used was about 13 minus 2.5 for my graph, times 10 negative 3 over 5.3 minus 1.4. Ooh, this is in volts. So it's in coulomb. Don't forget the negative 3. And that will give me about 2690 times 10 to the negative 6. So that's what I got, and I would probably write just 2700. Now if you check the mark scheme, they are the true value, the real actual best fit line is actually 2800. But they allow a range of plus minus about 200 microfarad. So anywhere, if your answer is between 2600 to 3000, you would be okay. So it's a pretty big range here to get your final A1 mark. But where do the other two comes from? The first one comes if you show like gradient and best fit line is very clear. Substitute a gradient, then okay lah. Then another mark actually comes from you attempting to draw a best fit line. They will say a reasonable attempt to draw a best fit line. So if it looks like a reasonable attempt, then you can get a B1 mark for drawing. What it means reasonable? It means I look at it, I'm like, yeah, I can accept lah, can lah, balance. Okay, so that's how you can do that. So don't worry if your value is a bit different than mine. Just as long as they're in range, you're okay. Next, use your answer to determine the additional energy stored in capacitor. You're like, maybe you haven't learned how to calculate energy. It's okay. I give you the equation first. Later you go and learn. So how do you find energy? There's two ways. One is E equals to half, not mc square, half qv or half cv squared. Because you know, Q equals to CV. You sub that in here, you get CV squared. So this is the equation you will use to calculate energy stored in a capacitor. But they want you to find the additional energy stored when the potential difference is increased from 6 to 9 volts. So there's going to be a change in potential difference. So here you have delta E. Which one should you use? The answer is you can kind of use the one that is less work for you. So we're going to use half CV squared. So delta of half CV squared. In other words, it's like saying half CV final minus half CV initial. So if you want to shortcut a bit, you can combine lah. So the C is the same because gradient is the same. C is gradient. And gradient is pretty much the same throughout the whole nice straight line. So we can just say, yeah, C is a constant. So I'm going to shorten this and say V final minus V initial. So like that lor. So C, you use what gradient you got. I'll use what I got. Okay lah, I use the correct value, 2800. Times 10 to the negative 6. Like, miss, why got times 10 negative 6? You be careful the unit here. Look on the top right. It's mu farad. Mu farad. So that's times 10 negative 6. Change in V is going to be 6 to 9. So 9 square minus 6 square. Yay. So you should get about 0.063. In other words, you would get 6.3 times 10 to the negative 2 joules. Write that down lah. Did I say 6.2? 6.3, sorry. 6.3 times 10 negative 2. Once again, your answer might be slightly different, but we'll see in a bit. 3 marks come from where? First one, do you know the equation? How to calculate energy? Okay, so I let you know lah. This is how we can calculate energy stored. Energy change is delta E. So do you substitute the correct values in? And lastly, correct answer. So depending on what you got, or you may have gone in anywhere in this range, 2600 to 3000. So as long as your answer is somewhere between 5.85 to about 6.75, you kind of be in range also lah. Oh, times 10 negative 2, sorry. Okay. So anywhere in here, you should be good. Okay, so that is this question. Nice and sweet to start us off with. Remember how to set up capacitor experiments. This is a pretty good overview of how we study capacitors, charge that is stored there, use current to measure, and things like that. Okay, let's look at the next one. This one looks more like capacitance now. This is ON10 P41, page 4. Define capacitance. So you already know, this question probably about capacitance. If you ever forget, just remember Q equals to CV. So C equals to Q, how much charge stored, and the potential difference across the capacitor. Now you have to be careful, is this capacitance are talking about parallel plate or just capacitance in general? It looks like it's capacitance in general, so you don't have to talk about the whole parallel plate thing. You can just say it is the ratio of charge stored. Stored where? They didn't say it's a parallel plate or sphere, so just say it's charge stored to potential difference across it. There we go. Nice 1 mark. This is a B1. Okay, ratio. So charge store over potential difference. Okay, next. We have isolated metal sphere has radius r when it's charged to a potential charge on the sphere is q. So you're gonna have something like this, radius r, and it has all these nice little charges stored. Positive. I just assume positive. Yeah, it can be other things. Okay, so this one is charge q. It's charged up to a potential of V with respect to ground. The charge may be considered to act as a point charge at the center of the sphere. This is like electric field kind of question. Correct? State an expression for the potential of the sphere. So it's kind of a bonus. You can remember your electric field. Wait a second, KQ over R. But maybe not use K lah. You write the full one, 1 over 4 pi E naught or epsilon naught. Over times R. Where's my Q? Q. So this is the expression for potential of the sphere, charged at a very high potential already. Okay, this expression is just a B1 mark. So this isolated sphere, now it's just by itself, keeping its charge with it, has a capacitance. Use your answers in A. This one. They give you a hint, use this. And B1, this equation, to prove something. Show that the capacitance is proportional to radius. So this is what you're showing, capacitance is proportional to radius. Don't forget, that's the end goal. And let's see, 1 mark only. So you can know that, Q equals to CV. Because when it includes C. But we know V is this equation for a sphere, a charged sphere. So we can plug that in here. So let me rearrange first. C equals to Q over V. Then I put the whole V inside. So this will be Q, this should be small q, over 4 pi epsilon naught R. And then I get Q's cancel off. So all I have is 4 pi epsilon naught R. The end. Wait, not the end yet. You must show that it is proportional to capacitance proportional to radius. So state the obvious. Is 4 pi epsilon naught a constant? Yes? Then say it out. 4 pi epsilon naught is constant. Proportionality, So that leaves with C proportional to R. Because if epsilon naught is not a constant, you cannot simply say C is proportional to R because we don't know. So here is just 1 mark. If you kind of did this and you conclude that 4 pi epsilon naught is constant, then you get a method 1 mark. Okay, so I'm asking you to see like a A0. That's just to tell you, you should get here with all the conclusion above. Otherwise, you might lose your M1 mark. Okay. Now, we have to find the radius of the sphere. The sphere has a capacitance C charged to a potential V. How to find QCV? But we don't know the Q yet, kind of. Yeah, we don't have information of how much Q is stored, so we can't use QCV. But we do know that C equals to 4 pi E naught R. And we can use that straight away to find R. No need to care about Q. Okay, very nice. So you know this is 6.8 pico. Wow, what is pico? Hey, this one please don't forget your AS prefixes times 10 to the negative 12. So this will be times 10 negative 12 equals to 4. You know what? Let me just divide. 4 pi. What is epsilon? Epsilon is a constant. You can find it in the calculator or the first page of every question paper. This is 8.85, or you can memorize it, I guess, times 10 to the negative 12, and this is your radius. So radius, about 0.0611 meters. I will write my answer in standard form, so 6.1 times 10 negative 2. Correct, right? Yeah, correct. Or 6.11 also can lah. So 3 marks all, you can guess. 1 is for final answer. 1 is for equation. Do you know which one to use? You prove it here just now. Nah, this one. Then you just use it here. Then your substitution. Did you sub in correctly all the values? Then you get that one. Okay, 3 marks for this. Next, what are we doing next? Wow, got so many more parts. Now you find the Q. So your Q, now you can do that. Q equals CV. Just now we cannot because we don't know Q. Now we are finding the Q. So we know the capacitance from before, right? Down here, 6.8 picofarads. So let's do the 6.8 over here. So 6.8 pico, negative 12. You forgot already, go and refresh a bit. Volts is 220 on the sphere. So that will give us 1.496 times 10 negative 9. Final answer, how many SF to write? 2 SF, 2 SF. Okay lah, 2 or 3 SF also can now. So I'll just put 1.5. You know, 1.50, why not? It's technically the same thing, but okay. 1 mark here. So this is just A1. Next, a second uncharged metal sphere is brought up to the sphere so that they touch. Wow, the combined capacitor of the two spheres is 18. Can combine like that one, meh? Can, why not? So if you are finding it very strange, like what is happening, here's what's happening. In the beginning, you have only one sphere. And then it has many charges stored on it there already. So this one is originally at how many volts? 220, I think. Yeah, so there's 220 volts with a certain Q stored on this fella. Now you bring another metal sphere closer. What happened? So this becomes maybe like this. They touch. So what's going to happen is all the charges in the first sphere will just redistribute themselves throughout this both sphere, because they are metal, so the charges can move around. So they will like kind of, they'll do something like this. Same total Q, but now you're at a different potential already. How do you find that? Okay, so I write here, same amount of charge. You didn't lose any charge, you didn't gain any charge. So what you can do is, Q equals to CV, because we know the new combined capacitance. Charge Q is the same, so we know that previously there's this amount of charge stored on one sphere, now become 2 liao. Okay, so this is 1.5 times 10 negative 9. New capacitance, 18 picofarad. And then you can use it to count the new potential, which is about 83.33 volts. So I write here, 83 volts. Means, actually the potential difference drop. At first it's 220. Now the potential difference at the surface of this whole sphere is going to be 83 volts. No more question mark. We know already. And you're the same Q. Now the next one is where you have to kind of brain a bit. The change in total energy stored on the sphere. Total when they touch. So in the beginning, you're going to have some energy. I don't know what, E, E1. Then after you touch together, you have a new E. What equation are you going to use to calculate the change in energy? Once again, energy can be calculated with half QV or half CV squared. Few methods. Which one to use? Q. Do we know Q? Do we know C? Actually, to be honest, you can use both equations. One is going to be a bit longer than the other. I'll show you the shorter one first. So I'm going to use half QV. Delta E will be, Q is the same, right? So half Q V final minus V initial or something like that. Okay lah. So half charge stored is 1.5 times 10 to the 9. So let's write that down. And what is the change in potential? At first it's 220, now drop down to 83 now. So 220, it's a decrease but We don't care about the positive negative sign, so just want to find the change. Although it should be like 83 minus 220, never mind lah. So if you do this in minus, you will get about 1.03 times 10 negative 7. Oh, it's a decrease actually, because it's supposed to be 83 minus 220. So here 3 marks. Final answer times 10 negative 7. That's A1. Equation C1, substitution C1, something like that. Yep, okay. So the long method, slightly longer, is if you use half CV square. Where is it? Ah, here. Because you have a different C and a different V for both leh. So I also write out the second method lah. Or you want to do half CV square minus half CV square. Okay, let's do the final one. So the final capacitance will be 18 picofarads. So 18 times 10 negative pico. Oh, 12. What's the final V? 83. Oh, so you do 83. Okay lah, we do properly. Final minus initial. Minus the initial. Initial capacitance given to us was 6.8 only. Very small. So 6.8 times 10 negative 12. Initial volt, 220. What you get here? You get a negative 1.03 times 10 negative 7, which is about the same thing. A bit longer lah, because you have changing C and changing V. Extra work. If I'm saying, Miss, why don't the first one got negative? That's because I swap. I go and say, initial minus final, just because I don't like negative sign. But if you want to be strict, you say final minus initial lor. Okay lor, we write final minus initial. Then you get a negative 1.03. Right? So that's the end of this question, I would say. Yeah, alright. That is this question about capacitance, how you can calculate capacitance of a sphere specifically. You ready for a last challenge question? Let's go and see what it's like. Okay, one more to end up this section. This is MJ18 P41, page 17, if you're looking at the handout over here. This one is a little bit different from the question before, because now they're asking about capacitance of a parallel plate capacitor. Wow, got difference eh? They want specifically parallel plate. So parallel plate capacitors, well, they kind of look like this. You have one metal plate, then you have another metal plate here, then the wire go out. The side view is like this lah, which is why the symbol of capacitor is, parallel plate, like what you all do in electric fields, got two metal plates. So you need to tweak your answer a little bit already, because now you see it's going to be 3 marks. So you know that Q equals to CV, right? And you can rearrange that. Capacitance is Q over V. So you can say it's the ratio of charge stored over potential difference. But you must say charge stored where? Must be specific. So you say charge stored on one plate of the capacitor. So must be more specific eh. One plate of the capacitor to ratio of what? Q against V. So you say to the potential difference. I'm going to shortcut and just say PD across the plates. So it's kind of, it's really a throwback to electric fields. You're going to have a potential difference, delta V, across that side. So that's how you can think of it. So there's 3 marks here. One actually comes from you knowing this ratio of Q over V. So I just put here like ratio of charge over V. Charge to PD. This one I'll put a M1. Now the other details is charge where? Charge stored on one plate. Oh, you must be specific for parallel plate capacitor. And to potential difference where? Across the plates. So across the plates here is another A1 mark. Wow, 3 marks there, right? Like this. So if you see this is a bonus, but you must know that you're talking about capacitance specifically for parallel plates. Whoa, this one. Okay. Now, if you have not tried this example, pause the video now. Go try it first, then only come and look at it. Because this one, you'll find that you kind of have to read the question really carefully and to know what's going on. Okay, so hopefully you got to do that already, to at least try it out. Here you have a circuit, very similar to the one we looked at before. You have some battery power supply, capacitor, and an ammeter. When the switch is at X, so let's say we connect this way. The battery is connected to the capacitor. So what happens? Charging. The capacitor is charged this way. So what's going to happen, for example, is, current flow this way, or charges flow in the opposite direction. But never mind, charges flow this way. By induction, all the charges are going to gather here. Positive, 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 negative, 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 negative. So all the positive there will repel all the positive, so all the positive move the other side. In real life, it's electrons moving, but never mind, for current's sake, we'll just say this. So this is the charging loop on the left side. What happens if you disconnect that? Oh, there's no current now. So now the capacitor is just storing the energy there. All the charges are on the plates. But when you connect to the other switch, what happens is now you have the discharging loop. So here is discharge. What's going to happen to the charges? They're like, wow, we stuck here very long, we want to be free. So all this negative will just go back here. All the positive will move around. So you will lose all the charges at the plates and discharge a lot. So in the process, there will be a current flowing through this ammeter and you can measure a certain current. So that's how you know it's discharging. Okay, so remember the left side, charge, right side, discharge. Okay, depending on how you flip the switch. Let's see what we're supposed to do here. The switch vibrates. Wow, so weird. The switch vibrates. So there is X, then is Y, then back to X. Wow, 50 times each second. Wow. So it'll be like X, Y, X, Y, X, Y, X, Y, X, Y. So what the capacitor will do is, very cute one, it will charge, discharge, charge, discharge, charge, discharge, charge, so 50 times per second. Whew. And the current recorded is 4.5 mu m. Here, microamps. Okay. Determine the charge passing through the ammeter in 1 second. So 1 second, how many times has it charged and discharged? 50 times each second. So this is after 50 times later. So remember, charges only will pass through here. Charge passes through the ammeter when your capacitor is discharging. So every time you discharge, a bunch of coulombs will go through this ammeter. Discharge again, a bunch of charges go through. Discharge again, go through. So over 1 second, 4.5. How to find Q? Remember Q equals to IT. This one you gotta remember from AS, because one of the main ideas of what current is, rate of flow of Q. Okay, so we want to find Q. We know that in 1 second you have 4.5 mu is 10 to the negative 6, and in 1 second, why I draw so many lines? So this is just 4.5 times 10 to the negative 6 coulombs, total amount of charge that has passed through. Now a very important tip is, this is the amount of charge that goes through in after 50 times, because 1 second ma. So this is 50 times. 50 discharges later. This is the total amount that goes through. This is important because later they will poke you about it. So this is just 1 mark A1 here. Okay, lor. Now we come to the next part. Calculate the charge on one plate of the capacitor each time that it is charged. Now this each time, underline it, each time that it is charged. Just now we found a Q. That's actually Q total. After 1 second, which is 50 times. So if Q total is 10 to the negative 6 coulomb, each time that will be Q stored on each plate. That will be 4.5 times 10 to the negative 6 divided by 50. Because you already discharged 50 times, then the total add up to be this ma. So this one will give you 9.0 times 10 to the negative 8 coulomb. So you write here 9.10 times 10 to the negative 8. Now in 1 mark also, so A1. Okay, I'm going to pause here and go back to this picture again. So with that information, you can think of it this way. Once you charge, there's all this Q stored here. And this Q is 9 times 10 negative 8 on one plate. The moment you discharge, that 9.5 times 10 to the negative 8 will go and pass by this one. This amount of charge will pass by. Imagine all the dots pass by. This many dots pass by the emitter. So emitter sees that. But it's only for one discharge. Now do this 50 times. Each time you add another 9.9 times 10 negative 8. Discharge again, add another one, 10 negative 8. Discharge another time. So you keep doing 50 times. The total will be this one, 4.5 times 10 negative 6. Rewind a bit if your brain is like hanging like, how to brain this? Go and look at it and think through it very carefully again. Okay, anyway, let's move on. Capacitance, Q equals to CV. So here you know, we know Q. Which Q to use? You want capacitance, right, of the capacitor. So you know each time how much charge can be staying on the plate. So you're going to use this Q down here. So 9.0 times 10 to the negative 8. How much charge can be sitting on the metal plate? That will be C times, what's the V? Go give to us. The V. Check your circuit. V. God. Nah. This is in series with this capacitor, so there will also be 120 volts drop. You rise by 120, you must drop by 120. Kirchhoff's first law. So we know, 120, okay. We know info. So you divide everything out here, you should get a C of about 7.5 times 10 to the negative 10. Final answer 2 SF can already lah. You want to go 3 also can. So we go 7.5 times 10 negative 10. This is 2 marks, so 1 is for A1, 1 is going to be for a substitution. Because I think they really give you CV. Okay, sometimes they will give you QCV, but usually they want to see you plug in the correct value. So if you plug in, get substitution mark. Next, the final part. This one you have to brain a bit. The second capacitor, having a capacitance is equal to the one in C, now placed in series with C. Suggest and explain. Got 2 things. Suggest and explain what? The effect. What's the effect and why? So this is the what and the why. What's the effect? Why is that effect thing? The effect on the current recorded on the ammeter. How to draw? Imagine this. You have now the same circuit, but now you are connected to 2 capacitors, one here, one here. So these 2 caps are the same value, they have the same capacitance, but how does that affect the current, which is going to be on this side, measured by the ammeter? Now this one is a sneak peek preview of what we will be looking in the next unit right after this video. So get excited. How do you deal with capacitors in series and parallel? Here's a tip. When you have capacitors in series, you don't get to store as much charge on your plates. Why? Well, because you see, all these charges start moving thanks to the battery. Okay, let's connect the thing first. Let's connect. Okay, connect the circuit. So now we are charging. We are in the charging loop. All the charges will move, let's say here. All the negative is there. The negative will repel all the negative on the other plate. So all the positive gather here. Then where do the negative charges all go? All the negative charges will go here. They cannot cross over the capacitor. So repel and all the charges get pushed there. So it's quite limited lah. Like you can't do much here. It's just I push you, you push me, you push the next fella down the road. So that's what's happening here. Negative push positive. They push the capacitor, push all the way. So actually you don't store as much charge here. It's actually storing less at each plate. So that means when you connect to the discharging loop, pew, what's going to happen is all these fellas will move and these fellas will move and you will discharge and that's it. What happened to the fellas in the middle? These fellas will just move down. They cannot cross over capacitor. They are stuck. Okay, so strictly speaking, the negative charges are moving. So let me draw negative charge. So negative charge is moving. Orange one will go back here. The green color one, they are pretty much stuck in between. So inductance, they are stuck inside there. Okay, so they cannot come out. They just move around there. So what happens is your ammeter here will measure half the current of what it originally was. And that is partially because now your effective capacitance has decreased. So half the current means half capacitance because connected in series. I give you a preview how to calculate this. So the new capacitance combined together in series will be jing 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 jing. Are you ready for this? 1 over C1 plus 1 over C2 negative 1. Does this look familiar to you? 1 over C plus 1 over C. Looks familiar. You will find out more in the next video. How is this? Why is this? Where this equation come from? But for now, we'll just take it with a pinch of salt. We're like, okay. So you can say the total capacitance is half. So capacitance is the how much you can store, the certain potential. So total capacitance is halved. And you can say kind of like less total charge. Less total charge. Wow, I cannot spell. What happened to my spelling? Less total charge passing the ammeter. So there's less amount of total charge passing the ammeter, then you can say that is current will be halved. Don't just say decrease. If you can say half, you calculate and you say half. Okay. So if I do this calculation, 1 over 7.5 times 10 negative 10, 1 over 7.5 times 10 negative 10, I will get half, which is 3.75 times 10 negative 10 farad. So these two are capacitor together. They essentially kind of storing less charge. It's like saying, originally you have a very big plate. Here, very big plate. Now you have a small plate. So less amount of charge can sit there. It's like the equivalent of that. This one, wow, many can be there. Okay. That's kind of why the nature of it, because you have these sections where these charges cannot come out. All these at the edge only move around. Everything in between, they are just moving between the capacitors. Okay, so this one is 2 marks. Where is it? Capacitance half, current half. So capacitance half will be your first mark. Here, B1, half, B1. Wow, it's on red. If you feel like you're not convinced, you can try play around with some equation. So capacitance is calculated by C equals to Q over V. Right? So if your capacitance is half already, then your amount of charge passing will be kind of like half. And current also, current is what? In here, you're kind of measuring the average current about 1 over 1 second. So this one also half already. Your current lesser charge pass through in 1 second, lesser current. So that's what I'm trying to talk about over here. But the first one, we will think of it this way. The second one, I can think of that. Okay, so that's all for this question. This whole part where you can, intro to capacitor in series. You need to be able to use the equation to calculate later in the next section. But for now, this is the intro to capacitance and charging and discharging. So make sure you know how to think about all these systems working together. That's all for this video. I will see you in the next unit about capacitors in circuits, series and parallel.